Simcenter FLOEFD can drive innovation by discovering better designs faster, even during the early design stage, with its front-loading design capabilities. In this video, we will take a deep dive into design space exploration to show you how you can discover better designs faster with Simcenter FLOEFD. By using FLOEFD, we are able to gain important insight into the temperature variation and the flow dynamics of the IGBT module. And we want to see if we can improve the baseplate design to achieve better cooling performance. Thus, a new design was introduced. Varying the pin size, draft angle, and pin pattern, we are able to get this new baseplate design through an intelligent design space exploration to minimize the IGBT temperature as well as the cooler pressure drop across. Let's take a look how we did this in FLOEFD. We have seen that how the front-loading, multi-cat embedded, and easy project setup capability of FLOEFD can greatly benefit designers for CFD analysis. Directly in the baseline project, we can create a parametric study. As we can see, there are various options available depending on what needs to be achieved. We will choose the multi-parameter optimization, which uses an intelligent algorithm for design space exploration. Here, we can choose to vary the simulation inputs, annex expressions, assembly constraints, or part family parameters. Here's a parametric study that has been set up and solved. We saw right at the start how the base plate was designed with expressions controlling some of the features. In the input variable, we selected 4 parameters of interest: the diameter, draft angle, pitch of the heatsink pins, and the volume flow rate of the coolant. We then need to give a min and max range for each of these inputs. In the outputs variables, we can select the goals we'd like to optimize on. For this, I'm selecting the maximum IGBT temperature, which we'd like to minimize, and the delta P, which we'd like to also minimize. We can also define some constraints here if there are any engineering guidelines for operation. For example, the cooler cannot have more than a 0.17 psi pressure drop. I can also select other plot goals to compare the visual results. Finally, the scenario table allows us to select the optimization algorithm. As the delta P and maximum temperature are opposing goals requiring a compromise, we use the Pareto front to find an acceptable operating point. The software will then run 100 scenarios to calibrate the input variable sensitivity. Upon completion of the 100 runs, we can see the software has identified several optimum scenarios. Let's go to the study plot and see the 2 results analyzed plots. We see in the dependency plot, the maximum temperature is plotted against the delta P. We see that the infeasible design showing red, feasible blue, and optimum green. Here, the infeasible design means, although the design can be physically achieved, it is out of the constraint ranges that we set on the maximum IGBT temperature or the pressure drop of the cooler. From this plot, we can see we have not only one, but several optimum designs that are within both temperature and pressure constraints. We then can pick and choose which is the most cost-efficient, and so that we have the best out of the best designs. On the right, we have the parallel data plot. It plots the 4 input variables as well as the outputs. This is useful to study the trend and see the correlation between variables. For example, we see that the optimum designs can be achieved at 4 mm pin diameter, which is the upper limit of these parameters. This means if we are allowed to set the paint diameter wider, we might be able to find some new feasible or even optimum designs. Back to the scenario table, we can select scenario 99, which is A optimum. We can right-click and create a FLOEFD project out of this optimum. Jumping over to this design, we can see the paint are much denser and also the paint diameter are wider. Let's compare the results. We can see there's less circulation in our new design, and also the temperature of the coolant at the outlet is higher than the original design, meaning the coolant is taking away more heat. And we can also look at the pressure plot. We see that we have a less pressure drop than the design before. We can also use the numerical data to compare the results. From this table, we can see clearly that our maximum temperature drops and the delta P decreases as well. Performing this parametric study, we can obtain not only one, but several optimum designs, allowing the user to take this newfound knowledge to look into the possible trade-off of IGBT maximum temperature and pressure drop of the cooler.